Hello everyone, welcome back to Spectrum Classes. This video is in continuation with the molecular orbital term symbols. And here in this video, I am going to discuss about the molecular term symbols for boron homodiatomic molecule and oxygen homodiatomic molecule. So first we are going to discuss about the homodiatomic boron molecule, and then after we are going to discuss about the oxygen molecule. So here is the molecular orbital diagram for boron homodiatomic molecule. So here the pi orbitals are low in energy as compared to the sigma orbital. These two are bonding molecular orbitals, and in this case, if suppose I am having B2 plus, so first I will start with the B2 plus. Here, if I am having, instead of B2, I am having B2 plus. So what will be the electronic configuration? So we are having one electron only. And if we are having one electron only, so here lambda is equal to 1. So lambda is equal to 1, and it gives me pi symbol for this orbital. And now its spin is s is equal to 1 by 2. So 2s plus 1 will be equal to 2 into 1 by 2 plus 1. This gives me 1 plus 1 is equal to 2. So spin multiplicity will be 2. Now what about this is G-red or un-G-red? So as you know, pi bonding molecular orbitals are un-G-red, and here you can write down it un-G-red. So this will be the molecular term symbol for B2 plus. So it is simple, right? Now coming to the B2 molecule. So here, as we did for B2 plus, we cannot do this for B2 only, because we are having two equivalent electrons, right? Here you can see one is in lambda plus 1 and the other one is in lambda minus 1. These two electrons are known as equivalent electrons, and for these equivalent electrons, as I told you earlier, in atomic term symbols we have to identify number of microstates. So let's start with the microstate here. I hope this point is clear to you. If we are having two equivalent electrons or more than two equivalent electrons, then we need to go for microstate. So formula for number of microstates is factorial n, factorial e, and factorial h, where factorial n is the total number of vacancies which are available. So in two pi orbitals, we can accommodate maximum 4 electrons, 1, 2, 3, and 4. Here you can see, right? So in this manner, you can accommodate maximum 4 electrons. And how many electrons are available with us? We are having 2 electrons. Number of holes are there, so n minus electrons is equal to 2 holes are there. So in this manner we are going to calculate our number of microstates. So number of microstates are factorial 4 divided by factorial 2, and this gives me 6. I am going to explain it for you, and here in this manner you can understand. 2 2 are 4 and we will get 6. So here we are having total 6 microstates for this. Now we are going to draw these microstates. So here I have drawn 6 blocks since we are getting 6 microstates. One of the pi orbital is having lambda value is equal to +1, and the other pi orbital is having lambda value -1. Now we are going to arrange the electrons in these 6 microstates. So first, as I told you in my atomic term symbols, so n minus 1 we will start with this, and up to half we have to go. So n is 4, minus 1 is equal to 3. So 3 electrons should be in this manner, and next is 2, which is the half value. So 2 electrons are in this manner. These are the up spins, and after this we are having the down spins similarly. So here, what about the next second electron? So second electron in this manner we are going to arrange. This I am not going to explain here because I have this is a trick and I have explained it in detail in my D2 term symbol video. So here you can see in this manner we are having 6 microstates for these 2 electrons which are possible, right? Now we are going to calculate the sum of lambda value here. and sum of the spins. So lambda, how we are going to calculate? So both the electrons are in my +1 state. So +1 for one electron and +1 for second electron. So in this manner I get +2. +1 for one electron, -1 for another electron, I will get 0. Similarly, where two electrons are in two different orbitals, we are getting 0, and when these two are in same orbital, then we are getting the sum. So here -1 for one electron, -1 for second electron, so -2, and here again 0. So this is how you can calculate your summation of lambda. Now coming to the summation of spins. So this is plus spin if it is up, and for the next one it is -half. So these two are cancel out. We are having 0. Similarly, one up, second down, we are getting 0. Similarly here 0, and both are down, we are getting -1. Now we are going to arrange according to their microstates. So here I am going to arrange the microstate in this tabulated form. So here you can see the important point is this. In previous case, we are having this ml plus L2 minus L. Here you just try to understand in case of atomic orbitals, we are having plus L2 minus L. But here I have written and. So this is important. Here I have written and, means I am having only two values, that is plus L and minus L. No values other than that. But similar to atomic states, we are having this S plus S2 minus S, means plus S comma S minus 1 comma S minus 2 and so on up to minus S. So with the unit of one difference, we are moving plus S to minus S. So for my lambda, I am having +2 and -2. This is done. So plus -2 will represent one microstate. Here we are having 0, 0 and 0. So this is my another 0 state, and it is 0 state. Now you may ask, if you have assigned one state as 0 state and here you have assigned three states as 0 state. So I am explaining it on the basis of the spin. So here spin is 0 and 0 for both the cases. But here in this case I am having +1, then 0 and then -1, means plus S to minus S 1 by 1. So here +1, -1 and 0. These three states corresponds to 1. S is equal to 1. For these three we are having the same value of lambda. Therefore I am having 3 zeros for S is equal to 1, +1 to -1, right? And similarly here 0 is the spin and 0 is the lambda. So this state represents lambda is equal to 0 and S is equal to 0. So in this manner we are having three different states. Now assigning the term. For lambda is equal to 0, we are having sigma. For lambda is equal to 1, we are having pi, and for lambda is equal to 2, we are having delta. So here we are having, so this is the lambda and this represents the delta state. Here this represents the sigma state, and again this represents the sigma state. Now we are going to represent the multiplicity. So S is equal to 0 means 2S plus 1 is equal to 1. And if we are having S is equal to 1, then we are having 3. Unlike our atomic term symbols, here we have to define our G-rate or un-G-rate, that is parity, and plus minus for sigma. This plus minus for sigma states, that is called inversion symmetry. So just to understand that, we are moving to the next. So this parity will be defined as we are having last two electrons in the bonding pi orbital. For these bonding pi orbitals, we are having un-G-rate, right? So we are having two even number of electrons. So if even number of electrons are there, then each are assigned as -1 for their parity, then we are getting ultimately +1. And if we are getting +1, it represents G. If we are getting -1, it represents U. So here both the electrons are in unzeroed orbitals, and since we are having an even number of electrons, therefore parity will be zeroed, right? Here you can see. So all three terms are assigned as zeroed. Now coming to the inversion symmetry. So it is little tricky to assign their inversion symmetry, and most importantly inversion symmetry is assigned for sigma states, not for other than sigma states, right? Now, how we are going to assign the inversion symmetry? So inversion symmetry you can assign by the tricks, but before giving you the trick, I must explain it in detail, and thereafter I will tell you how you can easily predict whether it will be plus or minus. So let's start, and here we are using the quantum mechanical wave functions for assigning the inversion symmetry. This I have already discussed in my previous video, where we have assigned pi plus and pi minus. So here special wave function means these are for electrons in which orbital they are occupying. So here if both the electrons are in the orbital which are having value plus 1, then in that case we are having the special wave functions like this. If both the electrons are in the orbital which is having lambda is equal to minus 1, then the special wave function will be pi minus 1 electron number 1, pi minus electron number 2. Right. If you are having any doubt, then you can go and check my previous video to understand these special and spin wave functions in detail, right? So here psi special, if one electron is in lambda is equal to plus 1 and the other one is in lambda is equal to minus 1, then say this is electron number 1 and this is electron number 2. This situation is best represented by the state of superposition. Means we cannot all the time certainly say that electron number 1 is in plus 1 state and electron number 2 is in minus state. It can be possible that electron number 2 is present in the plus 1 state and electron number 1 is present in the minus 1 state. This kind of situation, when this cross is possible, we used to write this kind of normalized wave functions, and this gives the ideal situation in which both the electrons have equal probability to be finding out in plus orbital and minus orbital. So here 1 by under root 2, this is the normalization constant. So in this manner we are having four special wave functions for the two electrons. And for fermions I have given one video on fermions and bosons which are having half spins. We are dealing with the electrons and electrons are having half spins, therefore these are called as fermions. And for fermions, the total wave function should be antisymmetric according to the Pauli's principle. So this is mandatory to have total wave function as antisymmetric wave function. So what does it mean? Actually, the total wave function for a system is equal to, it's the product of special and spin wave functions, right? And to have antisymmetric total wave function, we need to have, if we are having a special wave function as symmetric, then our spin wave function must be antisymmetric. If we are having our special wave function as antisymmetric, then our spin wave function must be symmetric. Only in that case we are getting an antisymmetric wave function. How we are going to identify which one is symmetric and which one is antisymmetric out of these four? So these three are symmetric wave functions, right? And this is the fourth part is antisymmetric. If you are having any doubt in understanding the symmetric and antisymmetric wave functions, then you can go and check my previous video. I will give all the links in the description, right? Now coming to the next part of the spin wave functions. So here for this we are having a situation like this. Both are up spins. Electron number 1 is in up spin and electron number 2 is again up spin. Now this can be understood, and this gives us S is equal to 1. Like this is up spin, this is again up spin, and the sum of these two vectors we will get double of the resultant vector S, and this is equal to 1. Here I have written. Now situation number 2. In this case we are having our wave function down spin in both the cases, and here we are having the value of S is equal to minus. And these two are symmetric. both are symmetric. Now coming to the next, if in these two cases, again we are having the same situation. Electron number 1 is upspin and electron number 2 is downspin. Whereas here electron number 1 is downspin and here it is upspin. So for these two again we are writing the normalized wave functions which are having superposition states. So this is having plus sign and this is having again minus sign. And in this case, you can understand in this manner. So here, this is going in the positive direction, this is going in the negative direction, but the resultant will be on this. This is equal to 1, S is equal to 1. So this is a symmetric wave function. Here you can see. Now, this one is antisymmetric wave function. Here, this is antisymmetric. So here I have mentioned also. So this antisymmetric represents this situation and this symmetric represents this situation. So for these three situations we are having symmetric special wave function, and for this we are having antisymmetric wave function. So here for these three we are having psi spin as symmetric, and here psi spin is antisymmetric. Right. So what do you understand with this? So I am going to tell you in the next slide. Here you can see for this, suppose according to the Pauli's exclusion principle, psi total must be antisymmetric for fermions. Psi total is equal to the multiplication of psi special and psi spin. So either of the two must be symmetric and the other one must be antisymmetric. This is the condition actually. So psi total we can calculate like this. This is the special wave function for psi, and if it is multiplied by the spin wave function, so here this is psi special. So what you get, here you are having plus, it means it is symmetric, and here you are having minus, it means it is antisymmetric. Here I have mentioned. So psi special is symmetric and psi spin is antisymmetric. And this antisymmetry gives us S is equal to 0 and spin multiplicity is equal to 1. So here is your spin multiplicity. Here you can see. So this corresponds to symmetric wave function for special. And this is our, as I written earlier, this is special. So the inversion symmetry comes from here. So if our special wave function is symmetric, then we are getting plus sign here. So here you can easily understand, if you are having S is equal to 0, it means antisymmetric spin wave function. So our special wave function must be symmetric, and if it must be symmetric, then we are having plus sign, right? Now coming to the triplet state. So for triplet state we are having psi special. It is, here you can easily identify what it is. And what about this? So I hope you understand this. This is psi spin. So which one is symmetric? Which one is antisymmetric? Yes, you are right. So this is antisymmetric and this is symmetric. Spin is symmetric. So this symmetric spin gives us S is equal to 1 and spin multiplicity is 3 in this case for symmetric spin wave function. And if we are having this 3 here, it means R, this is symmetric and this is antisymmetric, and from here we can understand if we are having symmetric spin wave function, then our special wave function must be antisymmetric. So for 1 we are having plus and for 3 we are having minus. But guys, if we are having two different atoms and in that case we are having the sigma term, this rule will not be followed. Now coming to the oxygen molecules, and for the oxygen molecule we are having same type of term symbols as we have in case of B2 molecule. Here in this case we are having both the electrons in pi star orbitals, and if pi star is G-rad, so G-rad will gives us G-rad only, right? So these two are G-rad, G-rad and G-rad. And similarly, as I told you earlier, one means antisymmetric spin means our special wave function will be symmetric, and this means our spin wave function is symmetric. It means our special wave function will be antisymmetric. Now coming to the next, if we are having O2 plus means if one electron is removed from the oxygen molecule. So this is O2 plus. So one electron is removed. This is I pi and G red, right? So what will be the molecular term symbol? So lambda is equal to plus 1. Plus 1 gives us pi. This is G red. So here I am writing G red. What about S? S is equal to half. So this gives me 2S plus 1 is equal to 1 plus 1 is equal to 2. So this will be the, here I have written this term symbol. If I am having O2 minus, then guys you have to predict this O2 minus. So for O2 minus means oxygen is having one extra electron. So here we are having 3 electrons. Lambda is equal to minus 1, and if I am taking the lambda is equal to, so it is will be 1, and this represents the pi state. Now similarly 1 is the electron which is unpaired, so S will be 1 by 2 and 2S plus 1 will be 2, so 2 will be there, and this is in the G red molecular orbital. So again we are having the same term symbol for this. I hope you find this video helpful, and if you understand this concept which we have discussed here, please give me a thumbs up, share with your friends, and thank you for watching.